Hi everyone, this is going to be a short video about the introduction of the triple integrals. It's mainly just introduction of motivation and little interpretation, and there's not going to be of proof of any theorem or anything like that. So let us start with review of a double integral. So let me show you this. Double integral is mainly about the volume of the solid. So let me show just this much about the picture. So we're looking at this region R down there, which is a rectangular region in xy plane. And this top surface is given by the graph of a function z equals f of xy. So computing the volume of this type of thing is the meaning of the double integrals. Once with that motivation, and we have this Riemann sum definition, and there's straightforward mathematical definition, but main motivation is a volume. So the Riemann sum consists of these summands. So we divide xy, the region R in the xy plane, along the x-axis and along the y-axis irregularly, and then we use this height of the cylinder. So multiply the area down there, 2 deltas, times the height. When we choose the height, we have a freedom of choosing points in this tiny kjth region, and then apply it to this function value to get the height. The Riemann sum is adding all those things together to compute the entire volume, and this is the volume of a little piece of the solid as it showed. This next thing is going to be slightly different interpretation of this from the volume interpretation. So this new interpretation goes like this. I want to look at this object here, not the volume. We want to look at the mass and the weight of this thing. So if we assume it's a uniform distribution of a matter inside it here, and that means if I sample over here and over there, the number of molecules, for example, is always the same. So if you sample just about the same size here and there, its volume is going to be exactly this kind of directly proportional to the mass of this thing. So if you sample it here and sample it there, doesn't matter. It's going to, as long as it's the same volume, and it's going to have pretty much the same mass, and there is a proportionality involved in here. So if we change the unit of the mass, and we can pretty much regard the volume and the mass as the same thing here. So originally the double integral computes the volume, but adjustment of the units of a mass, we can interpret that volume as a mass of the solid as well. And one other thing that I'm throwing in here, so if you have, well, the mass is about how much the matter is inside a given volume, but if you introduce the gravity, then gravity pulls this mass toward to the center of the gravity, and it creates a force. So again, the relationship between the gravity and the mass is directly proportional if it is happening on the surface of the Earth. So by changing the unit again a little bit, we can regard this volume information pretty much equivalent to the force created by this object and pulling downwards. So that's the connection. We can look at this whole thing as a volume. The meaning of the double integral is a volume, but also we can look at this meaning of the double integral as a force created by the mass inside here, if it is uniformly distributed. The matter is uniformly distributed inside. So using that, we have an interesting interpretation of this meaning of this value, f of xy. So let's take a look at this building again. So down there, the bottom region had size delta xk, delta yj. Before we're calculating the volume of this one, and I was trying to explain that we can just regard this volume information as a force information with a change of unit of mass and things like that. So the volume is creating exactly the amount of force exerted to this bottom region because of the gravity. So next thing we're going to consider is something called the pressure. So here, the idea of the pressure is this force applied to the certain region And if you divide the magnitude of the force by the area of the region it's applied to, and then it tells you how much of the force is applied to the unit area in the bottom region. So kind of, if it is uniform, that gives us a very good idea of how much force is applied. So because we're sampling a very small area down there, and we're assuming this is kind of uniform, if I choose this part and that part, the magnitude of the force, we don't think it's going to be that different, so we assume it's a uniform. So we're going to measure that, this force applied to the bottom region, and if you take this quotient, it's going to give us the pressure. So we do rather accurate calculation of that estimate. All right. I'm not sure about that accurate part that I said, but it's a good way to look at this situation. So let's look at the force, and the force is exactly this height of this building. That height is f, the value of f, where this x star and y star is a sample point I'm choosing down here to get the height. Multiplied by the area down there, that's going to be the volume. The volume is directly proportional to the force that is created by the gravity, so that the volume is there's a proportionality, and that represents the force. And this much of the force is exerted to the bottom area, which is delta x times delta y. So if you divide it and these two cancel, then give you exactly k times the value f. So that's the pressure. So except that k part, which is constant, and adds anywhere we look at it here in the xy plane, that's always a constant. Therefore, this height is pretty much equal to the pressure. So if you're looking at the certain point x comma y with a high height, and it is implying that it is pressing down there with a lot more force than other points where height is small, that kind of makes sense. So we're interpreting this f as not as height, but pressure in each point in the region down there. So here's all everything together. So let's say the region R down there is not rectangular region like we have considered before, but suppose we have R, and at each point we have a pressure sign. The f of xy itself is really the pressure. Then if we want to compute the total force, because this pressure applied to this, for example, this little circular region, then because this let's say the circular region here is very small, such that this pressure doesn't change that much, then the force applied to that circular region will be this pressure times the area of the circle. So suppose we have sampled a lot, and adding those forces all together will compute the force applied to the entire plate of this round-shaped region R. So the meaning of the double integral would be pressure times sampled area of the sampled region. That'll be the tiny force add up all together. So that must be the total force. So the double integral of the pressure function will be the total force applied to this plate. And that's the new interpretation of the meaning of the double integral, not just a volume, but the force applied to this plate. So that was the review and the slightly different interpretation, the meaning of the value of the double integral. So let me introduce the motivation of a triple integral. So I think I showed that before, some solid bounded by curved top, and I assume that it's a uniform distribution of the matter, so the sampling tells you, the volume exactly tells you what the mass is, directly proportional. Direct proportionality is the idea. So here what changes is that distribution. Suppose we have this rectangular region, so the top is not the curved surfaces. This is exactly z equals something. So this part is flat and horizontal and parallel, in other words, parallel to the xy plane. So we're looking at this solid and assuming that materials inside, the matter inside, is same matter, but it distributed differently. So if you sample it here, and maybe there's more molecules in a given volume than if you sample it here. So I labeled each side of the sample is supposed to be a very small sample inside this cube, and it is located at some position, so that's the sample. So if you look at the cube, we gotta sample some point inside there, And the volume of this thing is not going to be directly the mass of this thing because the distribution is different. So we have to come up with some sort of a density inside, and how much stuff is inside if I sample that much of a cube from this location. So that's the idea. So we have a density function. If you sample it here, we know how much of a density, how much of the matters are there, and how much of the matters are here. So if we have density function, and we can calculate the mass of this thing, and therefore we can calculate the mass of the entire rectangular box. So let's introduce the density function. If I have a position x, y, z, this f of x, y, z represent the density. So let's review the meaning of density. Here is the idea of the density, and we're going to sample and certain size in terms of volume, and then we count or the amount of matter inside and divided by the volume. So this will tell us if it is a uniform distribution. This will tell us given unit volume, like cubic centimeter or something, and that could be the number of molecules, or directly you can translate it into mass. And the tricky part is the density is not about just volume. It has to be the point idea. If I give a point and we assign this density there, that can be mathematically defined by taking the limit. So if this delta Vijk is the volume of that cube that I showed before, the little cube that I showed before, so if we sample, let's say the central location of the volume, that little cube is x comma y comma z, and if you take a smaller and smaller size of a cube around that center x, y, z, and what's going to happen to this ratio? How much of the matter is inside to that small volume? That if the ratio converges to something, and that's the idea of the density. So again, if a sample is small enough, and you can take that as a good approximation, and assuming that because it's small, it's a uniform distribution just in that tiny cube inside, and we can just simply multiply the density by the volume, that small volume, to kind of get a good approximation of the mass or amount of matter inside that small piece. But that will be the mathematical definition of a density, the limit of the quotient of the amount of matter in a given volume, sampled one. So here I wrote it down, what I just said. So if you sample the small size of the cube, and if you assume just in that little cube the distribution is uniform, the mass will be the density times the given volume. And the density is sampled at some point. Of course, if you sample different points inside that little cube, it changes, but doesn't change too much. Somewhat, this is going to be a good approximation of the mass of the little thing. So important part is that it not only is just a good approximation for that tiny cube, the entire rectangular box, but if we use this sum up all this mass of the tiny pieces, it's actually a good approximation of the total mass. There's a difference in here, but that is negligible, and then this triple sum really picks up a very, very accurate approximation of a total mass. So that part has to be justified mathematically, but that's what happens. Then, of course, whenever we have this type of the Riemann sum and consider whether it converges as we partition that x, y, and z along the sides irregularly and arbitrarily with this free choice of the points, whenever they converge, we say the integral exists, and then that integral is denoted like this with a 3 integral symbol. And B is that rectangular box that I showed you before, and this F represent the density. So if you integrate density function over a solid, that measures the total mass of the solid given. So that's the definition. The next part is going to be this connection to the triple integrals. Not the triple integral, connection to the iterated integrals. So I organized the Riemann sum that I showed earlier in this way. So let me show the original Riemann sum that I showed a minute ago, which was this one. It's a triple sum, and this density, and sample that in a certain part and multiply by the volume of this thing. So what we're going to do is that we're going to make a certain choices of these xy points and then kind of regroup this inside as a sum where k varies and relatively this I and j are fixed. So that's what this is. The way I organize these points inside the sample points is somewhat I got rid of this k index and a k index there, but I kept this k index there. But this is going to be the free choice. That means it does this choice of the points for x and y coordinate does not depend on k value. For all this k given I, j, we're going to choose the same xy value, but z value is going to change. So let me explain a little bit more about why this k disappeared here. And again, it is about the way I choose the points and a sample point for each cube, and then I can get rid of this k. And let me use this diagram to explain the choice of my points x, y, z. All right, this is the picture. There are lots and lots of cubes inside that big cube, but we organize it in this way. For given an I and j, there is this ith interval along the x-axis and jth interval along the y-axis. So we're going to relatively fix that I and j. First, consider given that I and j, we consider all the kth interval along the z-axis. So we stack up all this thing. So this is not varying, because we're looking at this rectangular box. This really goes from the bottom of that big cube and the top of that big cube. And then we divided all the z-axis into intervals like this. So we have a freedom of choosing all those points in that different cube. So that's going to be the first cube here, and that's going to be the second cube and along the z-axis. So we actually chose all the points such that they line up vertically, so they all have the same x-coordinate and y-coordinates. So as we add up along the z-index, this x and y coordinate sample point, it doesn't change. So we have that freedom of choosing that points, and because we assume the integral exists and Riemann sum, part of the definition of the Riemann sum, and choosing these points are free. So we can choose it in this way. So that's why we have all these three coordinates. This only first two only has I and jth coordinate. It doesn't matter what the k is, they're always the same for given I and jth. So we can regroup this sum like this, and the reason that we're not having this delta xi and delta yj in there, again, this one only has I and j, and as k varies, it's going to be always constant. So it can be factored out from this sum. Then we have this form. What's nice about this one is that we are looking at this x star and y star as constant relative to z value. So we're only considering this one summation with this delta zk. So that's exactly the one variable Riemann sum. So if we can take the limit just for that part, we can change that to the one variable integral. So this is how what I mean by that. If I just take this, just to separate this portion and take the limit, and then it's going to turn to a one variable integral like this, and that's exactly the definition of the Riemann sum. No, excuse me, the definition of the integral, the one variable. So where these and that x star and y star is a constant, and the integral against the z value. So with that limit, it's going to look like this. So if there's this Riemann sum doesn't have limit in it, but if you apply the limit just to that part, and this will approach exactly to this quantity, where n and m is not approaching infinity, n and m up there is just fixed, and I and j are fixed. All right? So if p approaches infinity, for example, then it's going to approach that part. So we pull out nice integral form, and this one no longer has z value in there, so this is a function of x and y. So we can treat this sum as a double Riemann sum, therefore it has an interpretation of a double integral. So what you should be careful about is that we want to turn this Riemann sum into an iterated integral. And if you think about the way we did it in a two-variable, we used something called Fubini's theorem. In my earlier video, you see that Fubini's theorem is taken as a serious part when we make this transition from double integral to the triple integral. And in that video, I explained it's all about the order of operations. So two operations we are considering here is this triple sum versus limit. So the original definition of a triple integral is that we do the sum first and limit later. But what we just did it here is somewhat separated a certain part of the limit and acted on their inside first, then did the sum later. And then it seems like we're going to turn into this triple sum is going to approach the following triple integral. So if we allow this different order of operation, sum first and limit later, or limit first and sum later, if that's allowed, it's easy to turn this summation into this triple integral. So all I did here, this inside integral taken as a function of x and y, and when you do that, and everything in terms of y at I and j, and it is sensitive that we need to have this x and y coordinate only in terms of I and j like that. But with that, we turn this inside as a function of x and y. Then if we change this one as a function in terms of x and y here, like that, then we see this as a function of x and y. And then rest of the part, it's just double integral and Fubini's theorem. So here, I'm not just using Fubini's theorem for double integral here. This part, mixing this inside limit first and then sum later, and sum first and limit later. So all together, I am using the Fubini's theorem for triple integrals. But with that given, the Fubini's theorem given, this triple sum is going to approach this triple iterated integral, which is supposed to be equal to the triple integral. So let's take a look at this example. So we're looking at this density function x, y, z squared, and over this box B, which has these limits. So there's no x and y's here depending on each other. There's absolute bound from -1 to 1, -2 to 1, -1 to 3. So that's going to be that rectangular box we have seen before. So this whole thing will measure the mass of this object, where the density of the matter is given by this function. For example, if I choose 0, 0, 0, then this x, y, z squared is going to be 0. So if I sample around the origin, the density will be very, very small. So if I really sample small enough, there will be almost no matter inside that little sample. That's the meaning of this x, y, z squared. But if you stay away from the origin somewhat, and x, y, and z are all big enough, then there will be a lot of concentration and a big concentration of the matter in that part. And it's going to pick up and more mass. So to calculate this, we just simply turn this one into triple integrals. So keep saying the wrong thing, is turn this triple integral to the iterated integral. All right? So here's a triple integral, and we put all these bounds in this order x first out from the outside, and y and z in this order. So because inside the z integral is first, we integrate, keeping x and y as constant. If you integrate along z, that z squared is going to be 1/3 z cubed, and it's evaluated at -1, and 3 is -1. It's missing here. It's typo. But you can evaluate that and one at a time. But it is indeed just like the two-variable case. These limits of each of this iterated integral is absolutely absolute constants, and these functions are all nicely separated by multiplication. Then they all pass out each other and becomes just the product of a three integral, just like the two-variable case. So they look like this. X and y and z all separated over these limits. These are absolute constants. So the total mass will be the this quantity here, product of these three quantities. Okay, so that's how you turn the triple integral to an iterated integral. And as soon as we do this integral inside of first, and this triple iterated integral turns to a double iterated integral, and at the beginning of this video I gave an interpretation of the meaning of the triple and double iterated integral, not as a volume, but something else that was a total force. So as soon as we evaluate inside the z integral, maybe we can naturally turn this one as a force or something. So that's my next attempt to make a nice connection to the double integral interpretation. So here's a bit more notation. Since when we do this inside integral, we have this x and y as a given constants, and do the integral again along the z. So if we have a different value of x, y, of course that changes. Therefore it is considered as a function of x and y, and it is one of the standard result that this is a continuous function in x and y, if this f three-variable function is a continuous function. So we can rewrite this triple iterated integral, it's a double iterated integral like this. So interpretation of the double iterated integral or double integral was the following. If this is a pressure function, this whole thing is supposed to pick up a total force function. So I'm going to make a first connection with this total force and how this can be interpreted as a total force out of this mass function. The meaning of this triple integral being mass, how would it make a transition from this mass to a total force? That's my first thing to do. Here's a little bit of this summarize the situation from big picture here. This whole thing is our box B, where x varies from A to B and y C to D and z from Q to R or P to Q, whatever that I labeled it here. So the triple integral means it's a total mass. I'd like to make a connection to the total force, of course, if I introduce the gravity down there. That arrow indicates the gravity. And then it's going to create a total force exerted on the bottom plate. Because we assume it's a non-uniform distribution of matter inside, if I choose this point here, this total mass, the mass stacked over that given point over there, will be different from the point over here. And although it has exactly the same height, because of the non-uniform distribution, maybe it's lighter on that part, and the force is going to feel is going to be directly proportional to the mass stacked over there. So in that way, it kind of makes sense that interpreting the total mass, you're connecting the total mass to the total force. So this is the whole thing together. What I just did is that we're looking at this as the total mass, but we can kind of consider this magnitude of the total mass is exactly the same as the magnitude of a total force if we change the unit of mass again. So changing from total mass to total force makes sense. And if we're staring at this double iterated integral or double integral and we're setting it with the total mass, that makes perfect sense if this g is a pressure function. That was the interpretation, new interpretation of a double integral that I did in the beginning of this video. But here's I'm being a little bit more careful here. If this is a pressure function, then definitely this whole integral is a total force. But this whole integral value being total force doesn't mean that g of xy is really the pressure functions. This is just a number, and you can come up with some crazy function here. All total double integral value happen to be exactly the total force. But it is indeed that g of xy is a pressure function, and I'm saying that this being the total force doesn't necessarily imply that g of xy is exactly the pressure function that this gravity is creating. So I'm about to more carefully explain why this g of xy is a pressure. So let's think about what the pressure is, and then I'm going to sample the region down there, which has this interval xi and delta yj. To calculate the pressure, I've shown this picture before. I have to calculate the mass of this entire thing that's stacked up. That's going to be exactly the magnitude of that. It's going to be exactly the force that's exerted on that part. So the mass of this one, you have to just add up all the mass of each of this little cube that is sliced out by this nuts. And here I indicated that's the interval along the z-axis. So that's going to be the height of the first cube, and that's going to be the height of the second cube, and so on. So the mass of each cube will be the density, which is this represented by this f function, times the volume of each cube, which is this delta xi and delta yj and delta zk. So if you multiply these things, and that's going to pick up total mass in here, each of this cube along the z-axis. So that whole thing, if you sum up from k from 1 to p of this whole thing, is going to be total mass. And that total mass's magnitude is exactly the force that is exerted onto this bottom plate, which is this area delta xi and delta yj. So pressure is calculated, the total force applied to this area of the bottom region. So if you divide it, that's going to be the pressure. But the k varies here, and not I and j vary. So as k varies, this is treated as a constant, and it can be factored out outside, and that common factor cancels with this denominator delta xi and delta yj. So because these two things canceled out, what you're left with is just this sum without this delta xi and delta yj. So that's what's left with. So we've seen this one variable Riemann sum before with this star value, x star and y star value fixed. And what this one is approaching is this integral value, and by definition of our g function, and that was our exactly the g value, the integral of this f function along the z, where x and y are relatively constant. So if you follow through, the meaning of this whole thing was, again, the force divided, the magnitude of the force divided by the area of the bottom region. So that's the pressure, and the g of xy is supposed to represent the pressure. So that proves that not only that the triple integral, the double integral with the g function in it is a total force, so the inside the function, the integrand, is actually the pressure function. So again, this meaning of the triple integral is the mass of the volume B, where the f inside represent the density function. But to calculate that, you usually consider this triple iterated integral. And first thing we do is that we integrate it inside function. And as we do that, it changes to double iterated integral. And the interpretation of the double iterated integral inside there can be that inside function now turns to a pressure function. And all this interpretation is natural when we start from the total mass, and then equivalent, we switch that notion to a total force applied to the bottom plate. Then integrating along the z-axis here kind of makes sense to create the pressure down to the point. That was it. Thanks.